What we're going to do today is we're going to look at molecular compounds and compare their properties to that of ionic compounds. Okay, so we know from ionic compounds that atoms obtain a full valence orbit or full valence energy level by the transfer of electrons. Okay, and we remember the sodium atom will lose its valence electron because it only has one, and it's easier to lose one and gain 7. And in the process it'll form a sodium ion. And the fluorine atom will gain 1 electron because it has 7 valence electrons, and it's easier to gain 1 instead of 7. And it'll form a fluoride ion. And then because of electrostatic attraction, these two ions will charge and form an ionic compound. And we'll have an attraction between their two ions. Well, atoms have a second method for forming or obtaining a full valence orbit or energy level. And what they can do is they can not transfer their electrons, but they can share them. And this will happen between two nonmetals. So for example, if I have some oxygen atoms and a hydrogen atom, they could come together and they could share. Now shared electrons belong to both atoms. And so, for example, this hydrogen atom in the first orbit requires 2 electrons. So oxygen is sharing this electron with it, and this was its electron. So therefore it has 2 electrons in its orbit. Similarly, this hydrogen atom will have these 2 electrons, its own plus 1 shared from oxygen. And then oxygen has its 6, and then it has the 1 shared by this hydrogen atom, and the 1 shared by that hydrogen atom. So that gives it its 8. Okay, so covalent bonds are formed when atoms share their valence electrons to fill their valence energy. Shared electrons count towards both. Okay, let's take a look at another example. Combination of carbon and hydrogen. Hydrogen we know has 1 valence electron. Carbon has 4. So if we have 4 hydrogen atoms come and each share their electron with the carbon, then what happens is carbon ends up with 1, 2, 3, 4, 5, 6, 7, 8 electrons, and it fills its valence orbit. Each of these hydrogen atoms have their own electron plus 1 shared from the hydrogen, and so they each have 2. And so that gives them a full first orbit or energy level. Okay, we can show the sharing of electrons with our Lewis dot diagrams as well by having our symbol and shared electrons between the two symbols. And so this oxygen atom and the hydrogen atom share 2 electrons, 1 from oxygen, 1 from hydrogen. And this oxygen atom and this hydrogen share 2 electrons, 1 from oxygen, 1 from hydrogen. Okay, and we can see that there's our electrons for the oxygen, giving it 8. There are the electrons for the hydrogens, giving them each 2. And so as a result, they all end up with a valence energy level which is full. Now when we're doing these diagrams, we don't leave shared electrons as dots, but rather we show them as a dash. And so this dash would represent the sharing of a pair of electrons, 1 from each atom. Okay, likewise with our carbon and hydrogen. Okay, so here we have our carbon with its 4 valence electrons. We have our 4 hydrogens that are each sharing 1. So we can see the 8 electrons that belong to the carbon. And then we can see the 2 electrons for each of the hydrogen atoms. So we can see that they each have 2 for their valence energy. And again, we replace shared electrons with a line. So this tells us that this hydrogen and this carbon atom are sharing 1 pair of electrons. This carbon and this hydrogen sharing a pair. This carbon and this hydrogen sharing a pair. And that carbon and that hydrogen sharing a pair. So this carbon will have 2, 4, 6, 8 electrons. This hydrogen will have 2 electrons. And this allows each of them to have a full orbit or valence. So we can see here the 8 electrons that belong to the carbon, of which 4 are its own and 4 are shared, which allows it to fill its valence orbit. The 8 electrons for the oxygen, 6 of its own, 2 shared, which fills its valence, and similarly for the other oxygen. Again, we don't want to keep the shared electrons as dots, so we'll show them as lines. And so now because I have 2 lines, this suggests not a single bond, but a double bond, where I have 2 pairs of electrons shared. Okay? Likewise, we can have 3 pairs shared between 2 atoms. And so the carbon and nitrogen here are sharing 1, 2, 3 pairs. This gives the carbon its 8 because it gets 3 shared by the nitrogen and 1 from the hydrogen. It now has 8, filling its valence energy level. Nitrogen has its 8. Okay. And hydrogen has its 2. And so we can show a triple bond with 3 lines. Okay. Now, while we're looking at this, so one of the things to keep in mind, and this is just as a brief aside, there are a group of elements that exist as diatomic molecules. I'll never find a single hydrogen atom in nature. I'll find hydrogen as part of compounds, or I'll find 2 hydrogen atoms bonded together. And so we have a series of elements that are like this, and so we call them our Hofbrinkel acronym. Now, back to our bonding. With our bonding, so as we said, we can have a single bond where we share 1 pair of electrons, 1 electron from each atom. Our double bond where we share 2 pairs of electrons, 2 electrons from each atom, 1 for each pair. And we have a triple bond where we can share 3 pairs of electrons. And we have 3 electrons from each atom, 1 for each pair. Okay. Now, as we said, an ionic compound is any compound with at least 1 ionic bond, where there was a transfer of electrons from one entity to another. So if I have 1 ionic bond, there is 1 transfer of electrons, it's an ionic compound. Okay? And our example was our sodium fluoride. Transfer of electrons formed ions. The ions were attracted to each other through electrostatic attraction. Covalent compounds contain only covalent bonds, only sharing of electrons. There have been no transfer of electrons between atoms. And so these 2 basic differences allow us to establish some properties of the 2 different types of compounds. And they help to determine the physical properties of ionic and covalent compounds. Okay, so we can look at a nice little summary chart. So a ionic compound consists of usually a metal and a nonmetal, whereas covalent compounds only have nonmetals. Ionic compounds are formed through the transfer of electrons, covalent compounds through the sharing of valence electrons. Ionic compounds generally are all solid at room temperature. Covalent compounds could be solid, liquid, or gas. The melting point and boiling point of ionic compounds is very high, whereas the melting point of covalent compounds could range. Some covalent compounds have a really high melting point, for example, diamonds, and some covalent compounds have a really low melting point, for example, hydrogen gas. And so we have this very big range of melting points for covalent compounds, but ionic compounds, they're all high. Ionic compounds are soluble in water and they form an electrolyte. Covalent compounds may be soluble in water, but they might not be. But the key difference is they don't form electrolytes. Well, what's an electrolyte? An electrolyte is a solution which conducts electricity. A non-electrolyte is a solution which doesn't. Because although you're led to believe that water conducts electricity, pure water, if I just had water with just water molecules in it, it does not conduct electricity. We need to have ions. And so, therefore, if I add an ionic compound to it, it would form an electrolyte and it would conduct electricity. But if I added a molecular compound, there would be no ions, so it would not conduct electricity. The way we test this often is with a conductivity test. For a conductivity test, what we often will do is we'll hook up a battery to 2 metal probes and a bulb, and we'll stick the metal probes in our solution and see if the bulb turns on. And so if the bulb turns on, then it's an electrolyte. And that means that this solution will conduct electricity. If the bulb does not turn on, then it's a non-electrolyte. It means this solution does not conduct electricity. Often we describe our results as a bright bulb and dark bulb for a conductivity test. Well, let's use these properties now for what we really want them to use. Let's say you find 2 crystals on a lab bench and I ask you to determine what they are. And so we look at their properties And now we are going to use these. So we know that NaCl is an ionic compound because it contains a metal and a nonmetal. That leads us to believe that it's probably ionic. Glucose, which is C6H12O6, it only contains nonmetal atoms. So as a result, since I have only nonmetal elements, it's a covalent compound and it's not ionic. Now, solubility. We know ionic compounds dissolve in water, some covalent compounds dissolve in water. Since my crystal dissolved in water, I can't use solubility to say for certain that it's an ionic or covalent compound. Melting point. I know that ionic compounds have a high melting point, but covalent compounds can have both a high and a low. So I can't use that either. But because it does not conduct electricity, that tells me that the solution formed when my crystal dissolved was a non-electrolyte. When ionic compounds form electrolytes, covalent compounds would form a non-electrolyte. So as a result, the glucose is the crystal, or the crystal is glucose.